You remember last time we were talking about motion on general manifold, and you remember that the key new element last time was to add a potential term. Right? We added the superpotential H, and in terms of the superpotential H, we found that the Hamiltonian, okay, was apart from the stuff that we had before, which is d star plus d star d. We had t squared del mh del nh gmn plus t into del 2h by del m del n. So all these are with respect to the phi coordinates, the x coordinates, the coordinates in our space. And then we had this psi bar m psi n. You remember the structure from last time, right? So we had the kinetic stuff, and then the potential terms. Now, last time, right at the end of the last lecture, I hope it's okay that I'm just jumping into it without reminding you of the context and so on, just to save time. Okay, right at the end of the last lecture, we described how the ground states of this theory were going to look. And I told you I would justify that better this time, so I'm going to give you 5 or 10 minutes of that justification. Okay, as we saw last time, in the limit t goes to infinity, t is very large. As Shoaib asked, t goes to infinity, t equals infinity is sort of singular. But the spirit of this whole thing is to work at very large t and see what statements we can make reliably at large t. Okay? So, when t is very, very large, this thing here gives us a large potential, and clearly all low energy states are going to be localized around the points where that thing vanishes. Okay, but what is the place where that thing vanishes? That thing vanishes means del h square, mod square vanishes. We're a Euclidean manifold, therefore del h vanishes. It's a critical point of the theory, right? It's an extremum of h. Could be a minimum, a maximum, or a saddle point. Okay? Now we're in some general d-dimensional space. And so our h, we will could have extrema. So suppose phi I or xi mu is one of the extremum of the space. We will characterize the various extrema by the number of negative eigenvalues around them. So let's make that more precise. We can always choose some coordinates h around any extremum by appropriately choosing coordinates. We can always choose coordinates so that h is equal to sum over I lambda I phi I square. This phi I is some deviation coordinate from the minimum. What? These may not be orthogonal, but we don't care. We've not got some other notion of orthogonality. We'll just choose the coordinates in which this is true.
So you're saying the constant term can be removed and the linear term is 0 by the function?
The linear term is 0, and then we diagonalize the quadratic term by choosing the right change of coordinates. Okay. And, right. Now, we then work with these coordinates. Okay, so in these coordinates, in these coordinates, our Lagrangian, Witten tells us, becomes h is equal to. So this is the sum over all the various extrema. now, yeah, lambda I are the various eigenvalues of this expansion. Okay, so there's this extremum, and it has curvature lambda I in the ith direction. Some of them are positive, some of them are negative. Yeah, this is a good question. The metric, how do we know it's diagonal? So you're asking, why is this term diagonal? Yeah, it's probably because it's the same thing. Okay, good question. Let's try to figure it out. Okay. So let's see. So suppose we've got some point x, and we've got some h, which we do a general expansion for. Okay. So we do h, which is h of x naught, plus del I del j h by 2 xj. Okay. And in this expansion, we have gamma ij. Gamma ij is our metric. Okay. Now, let's look at the whole Lagrangian around this point. Okay. The whole Lagrangian is gamma ij. Gamma ij is now effectively a constant, right? Because gamma ij at that point. So we have gamma ij del I del j. That's the Laplacian term. Okay. Plus gamma ij del I del j plus this would be gamma ij del IH del JH. Plus T times del. Okay, that part we can always get rid of by redefining the size. So I'm not going to worry about that. Your question really is, how do I know that I can simultaneously diagonalize both these things? What?
Yes. This is a function of phi and this is a function of coordinate. So we can do that simultaneously, right?
H is a function of phi and this is a function of coordinates. That's probably right. So now let's see. So now, but wait, phi is the coordinates.
Yeah,
Phi is a function, H is a function of where you are. Okay. So, as you said, really what we can say is that H is equal to some alpha ij by 2 xi xj. This is really what is true. And then there is this gamma here. And you want to know whether it is possible to simultaneously diagonalize this. Okay, so let's try. So this thing here is gamma ij j del I del j plus alpha ij by 2, plus gamma ij by 2, alpha im alpha j n xm xn. Okay. X is phi. What?
You have taken the derivatives of x.
No, but this is del h, and the expansion around it is quadratic. Okay? So this is the harmonic oscillator directions. Right. And you want me to explain to you how we can make a change of coordinates so that this becomes this form. Yeah, it's a good question. Give me a minute. I know it's possible, but how does it work? Just.
So you want to diagonalize gamma and alpha both?
Yeah, we want to diagonalize gamma and alpha both, exactly. Or at least we want the net thing to become diagonal. Right. Okay, let's first let's first go to a coordinate system, a local coordinate system where this thing is unit metric. Okay, so we've done that. So then this is del I squared plus this form. Okay, now the question is it possible to take this object and diagonalize it by an orthogonal transform? Right, because orthogonal transforms are what keep delta fixed. Okay, but this will be true because this is alpha mi gamma ij alpha nj. I've taken to be diagonal. So it's alpha mi alpha alpha mj, where these are okay, nj, ni. Sorry, what?
You also made a coordinate transformation to make it diagonal, right?
Yeah, so after we made a coordinate transformation, whatever alpha is, we'll call alpha. Okay. So now every Hermitian matrix can be unitarily diagonalized, and every symmetric matrix, right, it's a real symmetric matrix, can be orthogonally diagonalized. Okay? But this is a real symmetric matrix. Alphas are real. Okay? And this is clearly symmetric because we're summing over I. Okay? Therefore, there is another coordinate change where I make this guy diagonal. It doesn't change this thing because it's an orthogonal coordinate change. Okay? And therefore, we've put it in the form del I squared plus the form we started. Is this clear? You know, you make very similar manipulations when you try to argue that the most general quadratic term built out of any kinetic term and any potential term is a bunch of harmonic oscillators. If you look at Goldstein or wherever you study classical mechanics, you'll see that a very similar manipulation is done there.
So you're saying there are kinetic term and the potential
Both are not diagonal, but all such things are in the end just a bunch of decoupled harmonic oscillators. What? Normal coordinates. So what we've done here is go to normal coordinates. Okay. So it's some famous thing, but we've just seen how it works. Okay. So now we've got this Hamiltonian here. And now I want to argue the result that I told you about last time, namely that the number of zero modes here, is that the only zero mode here is the one associated with as many p indices, as many occupation numbers of fermions as there were unstable modes. Okay? And the argument is very simple. You see, each of these guys, this is a bunch of different harmonic oscillators with spin terms labeled by this I index. Okay? So we've got this lambda I and its associated lambda I. We did that by also rediagonalizing the size. Okay? This you can check yourself. Okay? So now this is exactly the problem that we had in the one-dimensional context. For each different direction, we've reduced it to exactly the problem we solved in the one-dimensional context, where we've got a harmonic oscillator and a spin term. Okay? There you remember how zero energy states arose. It arose by cancelling the 0 point energy of the harmonic oscillator, which is always positive. Okay? Versus the spin energy, which was positive or negative, depending on whether you occupied the up or the down state. Okay? Now, this guy here was a function of lambda I square.
That term is exactly sigma 3, right?
This term is exactly sigma 3 in that direction. Exactly. Okay? So this term here was a function of lambda I squared, whereas this term here was a function just of lambda I. Okay? So, whether we occupy the up state or down state to cancel the energy depends on the sign of lambda. Okay? And of course, now there's some convention, but the signs are associated so that every time you have a negative, you have to occupy the fermion state. Of course, this occupy the fermion state, there's some convention, because who was psi and who was psi bar, that was up to us, whether we chose all down as vacuum, all up as vacuum. But we've chosen the convention such that every time you want to cancel the fermion the state, if lambda is negative, you have to occupy the thing. It's spin up. Whereas if lambda is positive, you don't have to occupy it. It's spin down. Okay? So with this choice of convention, the zero energy states are those that are occupied exactly as many times by fermions as there are negative eigenvalues. Okay? And so we conclude that associated with each critical point, okay, there is a form, the ground states of every critical point are P forms, semi-classically. Semi-classically, the ground states of every critical point are P forms, where P is equal to the number of negative eigenvalues associated with that critical point. Mathematicians call the number of negative eigenvalues associated with the critical point its Morse index. Or it's Morse label or something like that. So, okay, but we'll just call it number of negative eigenvalues. Okay? So, we call... so what we found was that we've got this manifold, we've got a bunch of critical points, and semi-classically, this guy was a P1 form, this guy was a P2 form, this guy was a P3 form, this guy was a P4 form. And what were P1, P2, P3, P4? They were the Morse indices, number of negative eigenvalues of these critical points, where P1 was equal to M1, and P2 was equal to M2, P4 was equal to M4, and so on. The Morse index of that critical point. Is this clear? Now, we know that the actual number of ground states in this problem, the actual number of ground states associated with P forms, is the Betti number BP. This we know because we solved the problem with no potential, and we proved that the number of ground states does not change as we change the potential. Okay? So we know that the number of ground states okay? But the number of ground states cannot be larger than the number of semi-classical ground states. Because the number of semi-classical ground states counts all the states with energies that are very low. Now, maybe some mixing will take these very low energy states and make some of them non-zero energy, as we saw with the one particle problem. But it can never happen. We've calculated a very good approximation that these are the only low energy states. Now, it can't be that some so suppose this is your spectrum of your theory, right? The spectrum of your theory is E. There's a bunch of states that are zero energy in perturbation theory, but maybe have some non-perturbative splitting. Then there's another bunch of states that have some fixed non-zero energy, maybe have some non-perturbative splitting, and so on. Now the non-perturbative splitting can't bring this down here, because this is some order 1 energy, or maybe some order T energy. Well, non-perturbative splitting can only give you e to the power minus T corrections. Okay? So, this bunch of states is on its own. It could be that some of them will split away and not be exact ground states. But the reverse cannot happen. So, the number of true ground states must always be less than the number of semi-classical ground states. Right? This is like an obvious statement. Now, but the number of true ground states is BP, and the number of semi-classical states is equal to number of critical points.
So if coupling constant goes to 0, what should be that as the difference between these two?
Between this and this?
If the coupling constant is going to 0.
In the limit, coupling constant is what? Is this T? I was talking in this T. So in T, energy difference between this state and that state will be determined by the volume of the manifold. By coupling constant goes to 0, you mean T goes to 0?
T goes to infinity.
T goes to infinity. So this is order 1, right? Okay, so let's see. These are all the non-zero energy states of this problem. In fact, it's order T. See, you see, because the ground state energy of this problem is of order T. Okay, so we had a harmonic oscillator.
That's why you were saying that it can't.
It can't, because this is order T.
Yeah, I was thinking, yeah, okay.
You understand it's order T, right? Because these are the various states in the harmonic oscillator that are either not a ground state or the ground state but the spin is misaligned.
Exactly.
Both of them have order T difference.
Yes. 0 and T.
0 and T, exactly. Right, so this thing is order T, whereas this guy is going to be at least perturbative in T, but actually we know it's going to be non-perturbative. It'll be like e to the power minus T. Large enough T, it's impossible for this guy to come down here. But it could be that these guys go away from exactly 0 to some non-zero guy. That could happen.
And that you were saying can happen by e to the power minus T.
By e to the power minus T. In fact, I'll give you 5 minutes on how that could happen. Okay? So, the Betti number must be less than or equal to the total number of critical points with p unstable directions. This is a remarkable kind of inequality, right? It's telling you that if you write down any function on a manifold, I know the topology of that manifold. Therefore, I know its Betti numbers. That gives me a lower bound on how many critical points of that manifold can have p unstable directions. If you think about it for a minute, it seems sort of totally non-obvious. Of course, mathematicians knew this before, but not too much before. And this is such a simple proof of that lovely theorem. Okay? So, this is an example of the connection between, you know how supersymmetry gives you beautiful mathematics. In this case, relatively simple, beautiful mathematics. When we go on in our study, we will find more complicated, beautiful mathematics. Okay. There's one more thing I wanted to say about this problem before we move on to considering higher supersymmetries. Okay? And the last thing I wanted to say about this problem was, we said here that these things could possibly split. Now, in the one-dimensional problem, because of Shoaib's question, we answered last time very thoroughly exactly how that splitting happened. You might ask, what is the analog to this in this problem? I won't work out all details here, but I'll tell you one or two things and give you a rough sketch of the picture. Okay. Tunneling between two different classical states are governed by instantons. So a question we could ask is the following. Can we write down all the instantons of this model? Okay? Now, if there are some people here who don't quite know what an instanton is, just ignore the next 5 minutes. Okay, we don't have the time to discuss that in more detail. But for those who do know what instantons are. So, instantons, for those of you who have heard of it, for those of you who have not, just switch off for 3-4 minutes. Okay. Instantons are solutions to the equations of motion of the Euclidean action. Okay? They're supposed to be, instantons are sort of like classical objects. So we're going to turn off all the fermionic fields. Fermionic fields are inherently quantum. Right? As we have seen, psi and psi bar are really a two-state system, which is an inherently quantum thing. Okay? Turn off all the fermionic fields equivalent, set them to 0. And deal with just the bosonic fields. So the bosonic fields in our theory were these phi or x coordinates. Okay? And the action of our theory had two terms that were purely bosonic. Okay? The action of our theory had two terms that were purely bosonic, and These terms were the kinetic term for the bosons and the potential term. Okay? So the action of our theory had dt gamma ij del phi I. This I called it x. Witten calls it phi, so I'm calling it phi. I hope you'll forgive me. Del phi j by t del t plus t squared gamma ij del h by del. Sorry, what? Oh, sorry, I didn't understand the question. I'm sorry. Let me call this lambda. Times lambda. Okay. And t is this parameter. Thank you. What? D lambda. Thank you. D lambda. This was our Lagrangian that we wrote down last time. I mean, the part restricted to just the bosonic fields. Now we go to Euclidean space. So when we go to Euclidean space, we change the action from being kinetic minus potential to kinetic plus potential. Okay? So all I do is put a plus here. Okay. Now, what I want to do is to find solutions to the equations of motion, Euclidean equations of motion of this problem. Okay. In order to do that, I'm going to do a little manipulation. Of course, we could do it more easily. But this manipulation is interesting and useful. You might want to call this the BPS manipulation. We'll understand why those names come about in a bit. Suppose, claim this action here is equal to S is equal to d lambda. And now I want to write del phi I by del lambda plus minus t gamma ij del h by del phi j, this mod square. By mod square of any vector field, I mean that vector times itself contracted with the metric. Okay, so if I expanded this out, there would be one such term with free index, let's say m, and then gamma I m. Is this clear? Plus or minus, and then I'm going to write down minus plus 2 d lambda del h by dh by d lambda. Why is this true? To see why this is true, let's open this guy out. It's the chain rule, exactly. When we open this guy out, we will get one term that's this guy with itself with gamma ij, that's this guy. Okay? Then we will get another term which is this guy with itself times a gamma ij. That will be this fellow. Okay? And then we will get the additional term which is 2 del phi I by del lambda del 2t, let's say plus minus gamma m j del h by del phi j, and then a gamma I m. Is this clear? Okay? These guys cancel each other out. And so we get plus minus 2t del h by del phi j del phi j by del lambda. Okay, but h was a function of phi. So h is a function of lambda because phi is a function of lambda. And the derivative, time derivative of h with respect to lambda works only because phi is a function of lambda. So we can use the chain rule and replace this by del h by del lambda. Because we've got a del h by del lambda here, this is a total derivative. Okay? So now you see something very interesting. you see that in the space of all Euclidean configurations, the lowest possible action configuration, the lowest, you could not have a configuration of lower action than a configuration that sets this to 0. Okay? Because suppose we want a configuration from a given initial point to a given final point. This thing is independent of path. It's just the difference of h between the 2 points. Is this clear? So we say that the action is less than equal to h phi final minus h phi initial. The action is always less than equal to that. Okay? And in fact, less than equal to, greater than, thank you. It's always greater than equal to this, and we can do it with either plus sign or minus sign. We can choose it for the sign where this is positive to make okay? To make a non-trivial bound. Okay? And this inequality is extremized for configurations that obey this is equal to 0. Okay? So now you can ask, are there configurations that obey that is equal to 0? Okay. Are there configurations that obey that is equal to 0? Well, what is that is equal to 0? So let's choose one of the signs. Let's say it's del phi I by del lambda is equal to T gamma ij del h by del phi. Let's put a minus sign. Now, phi j. Is this equation familiar to anyone? Particle moving in a potential. Particle moving in a potential obeys a second order equation. Exponential. I know what you mean. But that depends on the nature of h of phi. It's called gradient flow. You see, what is this equation? You've got a function h. And phi is moving in the direction of the vector field del h by del phi j. Right? Del h by del phi j is one form. We raised it with phi ij. So the motion of phi is in the direction of the gradient of h. So this is a flow that is trying to, well, depending on the sign, either increase or reduce h as rapidly as possible. Because you're moving in the gradient direction.
It is searching for the extreme.
It's searching for the minima, yeah. Okay. In fact, there is a very nice thing we can prove about such an equation. Suppose we look at d by dh, d lambda of h, with such an equation. Okay? Now, once again, we use this famous chain rule. So, d by d lambda of h is del h by del phi I times del phi I by del lambda. Or d phi I by d lambda. But d phi I by d lambda is this equation. Okay? So that's equal to del h by del phi I gamma ij del h by del phi j minus t. Okay? But this is always negative. This is always negative. T is some positive number. And the right hand side is a perfect square. So this is an equation when h evolves according to such an equation, when phi evolves according to such an equation. It's an equation that guarantees that you're always going from larger to smaller values of h. When does it stop flowing? When does this flow stop happening? It stops happening only when del h by del phi is equal to 0. So this flow is along a gradient direction from one critical point to another. You see, the flow starts and ends at critical points. Okay? And roughly speaking, you should imagine that this flow goes from a place where you're following some negative eigenmode, because you have to go down, to a place where you've got to a positive eigenmode, because as you were approaching it, you were going down. Okay? So you can sort of see that this is a solution where you're going from a maximum to a minimum, at least locally. There may be other directions where this was a maximum and that continues to be a maximum. Okay? But locally you're going sort of like from maximum to a minimum. Okay? Gradient flow is famous, is a very nice kind of thing. So, if you had very high friction in you were working in a system, classical system with very high friction in a potential, you would essentially be doing gradient flow tracking. Very high friction leads to gradient flow. Okay? It turns first order to second order equations to first order equations. Okay? So, in this problem, the solutions, the instantonic solutions of our problem are gradient flows from one critical point to another. This is very beautiful because we were looking for tunneling from one solution to another. But the instantons precisely do that, they connect one solution to another. What is the action associated with this flow? Well, the action associated with this flow didn't get any contribution from that plus mod phi squared. It got only contribution from the total derivative, and therefore was from the difference in h's. Okay? The flow is in such a direction that this action will always be a positive action, because it's h minus h, but we're going from higher to lower h. Okay? If you did the reverse, you would get the reverse sign in the action. So you will always get a positive action. Okay? So, the action of the instanton is the difference in the values of superpotential between these two critical points. Okay? If you remember,
Why you took the minus sign on the
I could have taken the other sign, and it would, if I had taken the other sign, then I would have got positive gradient flow, but my action would have been minus of that. So I will always get positive actions. So it's true, there are solutions both ways. Okay? By the way, I'm not going to discuss this, so maybe we can put it in a problem, Shuman. Are you keeping track of the problems? This week we'll send out a problem set. Okay. I am not going to discuss this just because we have to move on. But these solutions are not just solutions, they're also supersymmetric solutions. And which solution, whether positive or negative, tells you which of the two supersymmetries is preserved in the solution. Here we are ignoring the fermionic terms. Yeah. How are we talking about the supersymmetric part? So you should think of the solution as that bosonic coordinates are this and fermionic coordinates are like 0. Okay? And the way then we want to think of, check whether the solution is supersymmetric or not, is to calculate the variation of the fermionic part. The variation of the bosonic part will trivially be 0, because it's always proportional to a fermionic coordinate, which is 0 on our solution. But the variation of the fermionic coordinate is purely bosonic and may or may not be 0. Okay? So if you remember, there was one non-trivial psi variation in the supersymmetry variation equations. One of the psi variations was trivial, it was 0. And the other psi variation had two terms in it. A term involving h and a term involving phi dot. But what do we have here? We have a term involving phi dot, del phi by del lambda, and a term involving h. Okay? In fact, that coordinate, that thing was f. It was phi dot and f. And f, if you remember, was it was w, okay, which was derivative of the superpotential. Do you remember there was this I whose derivative was W? F was the auxiliary field, as you said. And when you work that out, you will check. Please, we'll try it as an assignment. All that remains is to check the signs and the numbers, right? Because the two terms are clear and that these two terms appear. Okay? Well, check that these two solutions are actually supersymmetric. One of them preserves one supersymmetry, the other one preserves the other supersymmetry. Okay. And the last thing I wanted to say about this, I won't go on in much more detail about this, is that if you did a path integral in the presence of a supersymmetric instanton, unless you put an insertion of a fermionic operator, you will always get 0. Why is that? You see, this, if we do the path integral in the background of this instanton, we're doing an integral over d psi bar and exponential of this action expanded around the instanton solution. There's also the bosonic stuff, the fluctuations of the bosonic fields, but that's not important for what I want to say. Now, if you do this integral without any insertions here, any fermionic field configuration that does not appear in the action will give 0, because the integral over that part of the fermionic field will be 0. Okay? But if the instanton preserves one supersymmetry but does not preserve the other, okay, then the variation of this instantonic configuration under the non-preserved supersymmetry, under the preserved supersymmetry, will be a 0 mode. Right? Because there is a variation, there's some change in the fermionic fields which does not appear in the action. Okay? So the integral over that part would give you 0 unless there was an insertion in your path integral involving that fermionic field. Okay? So all of this is to tell you, I'm sorry if you're not, we'll come back to more down to earth things in a minute, but just for the people who are following, all this is to say that if you try to calculate the transition element of e to the power minus beta, just transition between these two states, without some insertion you get 0. But you need some insertion with an operator which has one fermion. But there's a beautiful such insertion which has one fermion, namely the supersymmetry operators. So if you do this with an insertion of Q, you get something non-zero. And this then allows you to calculate the matrix elements of Q between these two states. It's very similar, all of this is very similar to what we did in the one-dimensional problem. You remember we had these effective instantons, that is the region from one solution to the other. You remember that the two states, two semi-classical states, spin up and spin down there. So if we just computed a transition element, we'd get 0, because the spin part made it 0. That's this fermion 0 mode. But if we inserted Q flipped the spin up, so we got something non-zero. That's the insertion of this Q. Okay, so this is the generalization of that way of thinking. And so by doing this, one can actually, and Witten has actually carefully work out the matrix element of Q between any two critical points and actually set up the problem to see which of the states will be lifted and which will not. Witten sort of ends this part of the discussion in his paper by saying that he conjectures that this is the correct final answer for the number of So now what we've got is some non-perturbative problem, and non-perturbatively some of these perturbative states might be lifted. Now there's no proof that if you do something even more exactly, there may not be further lifting. Witten conjectures, there will not be. So if you conjecture that, if that conjecture is correct, as it almost certainly is, then you find not an inequality between Betti numbers and something to do with the critical points, but an equality that's more complicated than the one I wrote down here. It involves diagonalizing or finding the Q cohomology of a Q operator, finding the Q cohomology of a Q operator, which is a matrix on the space whose dimensionality is the number of critical points in your theory, and whose matrix elements we know how to compute. So that then is if you believe that conjecture, it's a new expression for the Betti numbers of your theory in terms of a matrix of the cohomology of a matrix of whose dimensionality is the number of supersymmetric states, there's a separate problem for each P, and the dimensionality of the matrix is the number of critical points with Morse index P. You can write, physics gives you a Q operator you can write down on the space. I said it wrong. It's not separate for each P because Q links one P to another. It's a whole problem. The matrix is the dimensionality of the matrix is the space of the number of critical points of the theory. Physics gives you the Q operator whose cohomology you're supposed to compute, and when you compute this cohomology for each fermion number, okay, you get an expression that should be equal to the Betti number. Okay, so doing this instant-on calculation gives you a very non-trivial relationship between a problem of matrices linking the various critical points of the theory and the Betti numbers of the topology of the manifold on which these critical points live. It's very beautiful stuff. But we'll just move on here unless there are questions.
It will be critical points times the number of directions, right? And summed over all of critical points.
No. See, every critical point has exactly one supersymmetric ground state.
Yes.
So, the matrix is on the space of supersymmetric ground states, semi-classical supersymmetric ground states. And there is exactly one supersymmetric ground state per critical point. You have to choose how many fermions are. Is this clear? Okay? So the matrix, the number of components in the matrix is the number of critical points. And the physics gives you the supersymmetry operator, and what you're supposed to do is compute the cohomologies. And that will, from there, you'll be able to read out the Betti numbers of your manifold. It's a very beautiful, in my opinion, very beautiful connection between possible critical points of functions. Notice this is true not for one function, but for any possible function you can write down on this manifold. H could be absolutely anything. So it's a very non-trivial thing. It's telling you that you may think that if I've got some manifold, I can write down basically any function I want on it. But there are non-trivial topological restrictions of this function. If this has a Betti number, it must have at least those many critical points with P unstable directions. And moreover, there's this slightly deeper connection coming from the instantons. Okay, questions or comments about this? Okay, I think we will stop our discussion of quantum mechanics with two supercharges at this point, and move on to now to the study of quantum mechanics with more than two supercharges. Okay? Our main aim here, there are two or three. As with the first part, there are two or three aims, 2 or 3 points in this discussion. Always part of the reason for doing quantum mechanics in so much detail, one reason is that we want to understand all the ideas in a very simple and familiar context. That's always one aim. The second aim is to get new physics mathematics results. So we will do both of these. So the first part of our discussion will be on technical ideas. Okay? And the second part of our discussion will be then turning it to quantum mechanics on many coordinates, and we will see interesting new geometrical ideas coming out. complex manifolds and Kähler manifolds, and the connection between that and supersymmetry. Okay, but let's start. So this ends our discussion on quantum mechanics with 2 supercharges. Now, a question that you might ask is, in the study of quantum mechanics, could we have more Qs? What we had was 1 Q and 1 Q bar. Okay? Could we have more Qs? Could we write down a theory which has symmetry under more Qs and more Q bars than the ones we talked about? Okay? So, let us start trying. So, if you remember our Q operator was implemented in superspace by del theta plus theta bar del t. If somebody has the notes, please help me get all the I. And Q bar was equal to del theta bar, and was this plus I theta del t. And when we had our discussion, we also made use of these operators D, which were equal to del theta plus I minus I theta bar del t, and D bar, which was equal to del theta bar minus I theta del t. Now, a very simple idea one could have is the following. How about just giving these thetas and theta bars a label? So suppose instead of working in a superspace with 1 theta and 1 theta bar, we worked in a superspace with, let's say, 2 thetas and 2 theta bars. We'll start with 2. Okay? So, suppose we work with theta 1, theta 2, theta 1 bar. Yes?
Are there any constraint on this, how many levels we can take?
Okay, good question. You will see that if we want to write down non-trivial theories, we will not be able to write down non-trivial theories with larger than a certain number. Okay? But at this point, there's no constraint. Okay? We will see that. Theories that, okay, at some point you'll only be able to write down a free theory. Okay? You see, as you will see, what we're going to show is that when we have 2 of these thetas, we will have the ability to turn on a potential, and the kinetic term will have to be motion on a complex manifold. When we have 4 of these thetas, so totally 8, because 4 thetas and 4 theta bars. Okay? When we have 4 of these thetas, we will lose the ability to turn on potentials. And the kinetic term will have to be motion on a Kähler manifold. Okay? When we have 8 of these thetas, we will not have the ability to turn on a potential. There are some caveats to this potential business. I'll make it clear as we go on. And the manifold will be what is called a hyper-Kähler manifold. Hyper-Kähler manifolds are very, very tight. Okay? And then when we go to higher manifolds, basically the manifold will have to be flat. And there will be no potential. So now motion on a flat manifold with no potential is pretty boring, right? So that's the sense in which I mean free.
Why 2 raised to n only? Yeah.
Why 2 raised to n? We will see. It's sometimes possible to turn on other things. This is 2 raised to n is most familiar to most of us, because if you go down to quantum mechanics starting from 4 dimensions, in a 4-dimensional supersymmetric theory, the number of supercharges is 4 times n. Okay, that's why this is for most of us the most familiar case, because this is dimensional reduction of a 4-dimensional. But you can have lower. You can have, and we will see. We will see some of them. Okay. Okay. Okay, fine. But at the moment we'll start. At the moment we'll start easy. We will just take two of them. There'll be theta 1, theta 2, theta 1 bar and theta 2 bar. Okay. Now we can ask, so now the operators have become qi and qi bar, where I runs from 1 to 2. Now, theta 1 and theta 2 have nothing to do with each other. Okay, so it's obvious that so let's say Q1 and Q2. And other such things. Q1 bar and Q2 bar. Q1 bar and Q2. These are obviously anti-commuting objects. Just because the derivatives don't act on anything. Okay? Moreover, the algebra of Q1 with itself is unchanged from what we had last time. Just because I've called Q1, how does it change anything? Okay? And so what we've got is the algebra that this superfield representation implements the algebra Qi Q bar j is equal to delta ij 2 delta ij h, and all other anti-commutators are 0. Okay. Now, okay, at the moment all I've done is written down some symbols. The interesting question, as we indicated in the answer to Nikhil's question, is can you write down interesting theories that implement the supersymmetry algebra? Okay. Now, you might at first think that what we want to do is simply write down a superfield which is a function of theta 1, theta 2, theta 1 bar, theta 2 bar. And one can do that, and sometimes one has to do that. But you might ask yourself whether it's possible to do a little, when we're studying these theories, we want to study minimal theories. Now, if you write down a superfield that's a function of theta 1, theta 2, theta 1 bar, theta 2 bar, the total number of fields in your theory will be 16. Because in any term, every theta can either appear or not. So there are 2 to the 4 possibilities. That's a lot of fields. Right? When we worked with our minimal supersymmetry,
Yeah, you said that Qi Qj bar anti-commutator is delta Ij.
yes,
Okay, so if you take, so this is like what, H is equal to Q1 Q2 bar plus Q1 Q1 bar?
it's the same as before. Q1 bar plus Q1 bar Q1 is equal to 2H. And Q2 bar plus Q2 bar Q2 is equal to 2H.
Okay.
Right. Like
I see. So theta cancels out totally. That's why this is true.
why is this algebra true, you're asking?
No, I'm asking why H is not dependent on both 1 and 2 and only 1 and only 2.
Sorry.
Anti-commuter comes out to be del by del t. Iota del by del t.
I del by del t. Just like last time.
Yeah. It is independent of theta, so it doesn't matter which I you are in.
Yeah, it's just del by del t and that's Hamilton. Right? Okay.
The Hilbert space will be similar like tensor product of spin.
It's going to be a little more complicated. Let's hang on and see. Yeah, because there will be a few more fermions. Hang on and see. Okay. Yeah, but sort of similar in spirit. Okay. Now, the question is, how do we make an interesting theory with this, with this thing? As I said, if we just expanded a normal superfield, okay? As I said, if we just took a normal superfield and we expanded it, we would get 16 components. Last time we got 4 components. The scalar, 2 fermions, psi and psi bar, and 1 auxiliary field. Now maybe some of these 16 components will be auxiliary fields, but it still leaves a lot of fields. Right? Doesn't feel like a very pleasant theory to deal with. However, suppose we try the following. Suppose we try to look for superfields that are not the most general things possible, but superfields that obey the equations del bar 1 on phi is equal to del bar 2 on phi is equal to 0. Because del bar commutes with supersymmetry, okay, the transformation of phi before and after we put the del bar is the same. So this condition is a supersymmetrically invariant condition. Okay, so it's a condition that you can put and still implement the supersymmetry algebra because del bar commutes with supersymmetry, anti-commutes with supersymmetry. Okay, so if you do this, so these are possible superfields one can work with. And that allows you to construct theories, okay? Fields that obey this requirement are called chiral fields, chiral superfields. And the possibility of working with not the most general superfield, but superfield that obey a constraint, but one that is supersymmetrically invariant, is one new technical element in dealing with higher than 2 supercharges. Okay? So in the next class, I'm sorry, I'm going to have to go now. But in the next class, what we will do is expand on this. We will write down the most general superfield that obeys these conditions. We will understand the supersymmetry transformation properties of this superfield. Okay? We will understand that such a superfield is always a complex object. We dealt with real objects before. Our phis were real. The bosonic parts were real coordinates. Okay? We will understand that such a superfield is always a complex object, and that its complex conjugate of the superfield obeys the condition del on complex conjugate, del 1, not del bar 1. So that if you introduce such a field, you are necessarily dealing with complex fields, such that one field obeys one set of constraints, the other field obeys another set of constraints. And we will understand then how to write down kinetic terms and potential terms in such a theory, and then find our simplest such theories to answer Chintan's question. Okay, I'm sorry, but today I just have to go. There's some unmissable appointment at 3 o'clock, wherever. So, okay, see you people.